Good morning, students. My name is Rakesh Jha, and I am the faculty of mathematics. I am with Nuclei Institute, and here today we are dealing with calculus portion, uh, differential equations. So, differential equation, as we know that it is very important chapter, and it's not so difficult also. So, we will start from the scratch, and we will deal everything from the beginning. So let us see first of all what is differential equations. So in differential equation, as the name itself suggests, it's a kind of equation that involves one independent and dependent variables. So x and y may be dependent and independent variable and the derivative of the dependent variable. So here in this case, as the definition says, an equation involving independent and dependent variables and the derivatives, that is the differentiation of dependent variable, is called a differential equation. So for an example, if I am writing here dy by dx, so dy by dx is the differentiation wherein y is a dependent variable and x is independent variable. So y is a dependent variable and x is independent variable. So independent variable. In a similar way, if you write dx by dy, so in case of dx upon dy, here it will be just opposite. X will be here dependent and y will be independent. So either it should be dy by dx or dx by dy. As we have understood, an equation that involves a dependent variable and an independent variable and the derivative of the dependent variable is called a differential equation. So we have basically two types of differential equations. One is ordinary differential equation and one is partial differential equation. So we will talk about this one by one, but here I would like to tell you that we are dealing with ordinary differential equation, not the partial difference. It is beyond the scope of our syllabus, but I will just give you the brief idea about partial as well. So now moving to the next slide, what we find firstly, ordinary differential equation. So ODE, it is also called ODE. It's ordinary differential equation. Ordinary differential equation, it is an equation, differential equation where coefficients have reference to a single independent variable. So we have the reference of single independent variable only. That is the only major difference between partial and ordinary. In ordinary, more than in ordinary we have only one independent variable, and dy by dx, as I told you in the previous slide. So in case of dy by dx, y was dependent variable and x was independent variable. So here there will be only one independent variable. So for an example, see this case here, d2y upon dx square, this is nothing but second order derivative. Dy by dx, this is the first order derivative, and then cos x. What we are finding here is this y, x and x here both are independent variables. So we have only one independent variable. That is in the case of ordinary differential equation. But when you talk about partial differential equation, that is also called PDE. PDE stands for partial differential equation. So an equation, a differential equation, is said to be partial if there are two or more independent variables. Two or more independent variables. Two or more independent variables. So here We don't write dy by dx the way we have written. Here we write dou u upon dou x. Why? Because in partial we have different notations. So dou u upon dou x plus dou u upon dou y plus dou u upon dou z, this is equal to 0. This is a classic example of partial differential equation, because we find here x is independent variable, y is also independent variable, and z is also independent variable. So we find in this case more than one. So either two or more than two independent variables are present. Now moving to the next, now we shall talk about solution that is also called primitive of a differential equation. Actually, what happens if a differential equation is given, we have to solve it, and after solving it, we will get in the end two equations. One is general solution, and then after putting the values of the variables x and y, we get the value of c, and once we put the value of c, then we get the particular solution. So here two important terms we shall be discussing about, but before to that we should know what is a solution that is also called primitive of the differential equation. So finding the unknown function which satisfies the given differential equation is called solving or integrating the differential equation. So solution of a differential equation is also called primitive because the differential equation can be regarded as a relation derived from it. So this is very common. Now moving our attention to order and degree of the differential equation. So we have first order, second order, third order, and so on up to nth order derivative. So I will explain here. So if I talk about order of our differential equation, that I can denote with dE. So here we find like dy upon dx. This is the first order derivative, because here we have to differentiate just one time. If you take d2y upon dx square, then it's because two times differentiation, so we say here second order derivative d3 y upon dx cube. This is a third order derivative. In a similar way, we can have the nth order derivative. So dn x upon here it is a y upon dx raised to the power n is actually the nth order derivative. Nth order means n times differentiation. Here again, to make it clear that y being the dependent variable and x being the independent variable in this. Similarly for the other order derivatives. So in the previous slide we were discussing about order and degree of a differential equation. So what is order of a differential equation? Is the order of the derivative of the highest order occurring in the differential equation. So basically a differential equation can have one or more orders, one or more derivatives. It will have only one order, but the differentiation means derivative may be of second order, third order, of any order. So among all those, we have to find the highest order derivative. That would be called the order of the derivative. So if you talk about the previous slide, for an example, this example I'm talking about, this is the example of a differential equation, and if we are concerned about the order of this, so we find here this is second order, because 2 times, and this is the first order because this is one time differentiation. So among first and second, this is of higher order. So order of this differential equation will be 2. So order of the given differential equation is 2. So it is very much clear that one or more order derivatives is given in a single differential equation. Then among those orders, whichever is the highest one will be called the order of the differential equation. So now moving to the next here, we shall be talking about the degree of the differential equation. So the degree of a differential equation is the degree of the highest order of the differential coefficient appearing in it, provided it can be expressed as a polynomial equation in derivatives. So here one catch point is the derivative should be in the form of polynomials. So suppose for an example, we have here d3y upon dx cube plus d2y upon dx square plus cos x is equal to 0. Suppose this is an example of differential equation, and here I will write raised to the power 5 d2y upon dx square raised to power 5. As I have already said that in this case order will be 3 because we have to compare between second order and third order. The highest is 3, so order will be 3 here. Order will be 3. Now if you talk about degree, then whichever is the order here, in this case 3, we will go for the exponent of this. So exponent is nothing, so it's a 1. So degree will be 1. Degree is 1. Now we should not get confused with this second order derivative, because even if the exponent is a 5 here, this is not the degree because the order is 3. So whatever is the exponent of the highest order, that is called the degree. So in this question, find the order and degree of the following differential equations. We will see one by one. Here y double prime is 2 times derivative differentiation. This is 1 time, so here 2 time and here 1 time. So we know that between 1 and 2, 2 is highest. So we can say here order would be 2. Order will be 2. As far as degree is concerned, we have to see the exponent of the highest order. So exponent of the highest order is 5. So degree will be 5. We should not get confused with this. This will not be the correct option because exponent 6 is first order derivatives exponent, but we should not consider it. We will consider the highest order derivatives exponent. That would be called the degree. Now in this case, this is a third order, this is a second, and this is first. So of course in this case order is 3. Order is 3. But if we want to know the degree, here it's ln. Ln means log, natural log. So it is not in the form of polynomials. So wherever derivatives are there, third order derivative, second order derivative, first order derivative, we have to arrange them in the form of polynomials, and then we have to find the exponents of the highest order derivative. That is known as degree. So degree is not defined here. So degree not defined. Similarly, for the third question, order will be 2 because here 2 times and here it is 1 time. But if you talk about degree, so same logic will follow, because the first derivative here y prime, it is within bracket with a sign actually, so it can't be represented in the form of polynomial, so degree is not defined. Now let's talk about the fourth question. In the fourth question, order of course will be 2. Order is 2 because here this is second order and this is the first order. But as far as degree is concerned, this is not in the form of polynomial, but it can be transformed in the form of polynomial. How? If you, here it is root, here it is cubic root. So what we can do here? So here it's a 2 because it's a square root and this is the cube root. So we have to go for the LCM of 2 and 3. So LCM of 2 and 3 is 6. So we have to write 6 exponent both sides. So what will happen? Dy by dx, 2y upon dx square, and then here it is 6 upon 2, because we are both sides LHS and RHS, we are putting the exponent 6 both sides, so that the radicals will be removed. Here if you see here, dy by dx plus 3 and raised to the power 6 upon 3. Now 2 3s are 6 and here 3 2s are 6. So now if we will expand this, we will find here d2y upon a dx square raised to the power 3 is equal to, it will go as a plus b whole square. So it would be dy by dx raised to the square plus 3 3s are 9 plus 3 times dy by dx. Now this is in the form of polynomial. So we see here on both left and right side, the degree is 2 as already, sorry not degree, order is 2 because the second order derivative is there. This is the first order, this is again the first order. So order is already explained here. Now degree can be explained from the simplified form of this differential equation. So in this we are finding here d2y upon dx square, this is the second order derivative, this is the first order, this is again first order. So we will be concerned about the exponent of the highest order derivative, that is 2 raised to power, this is 3. So basically degree is 3. So degree will be 3 in this case. So order is 2 and degree is 3. Okay, now let's move to the next. Now we shall be dealing with the solution of the differential equation. As I have mentioned already, we have the general solution and the particular solution of a differential equation. So here general solution is simply solving the differential equation. We will talk about step by step what are the different steps for solving different types of differential equations. So here the solution of a differential equation is a relation between the variables of the equation not containing the derivatives but satisfying the given differential equation. In a layman language, we can understand that it is simply the solution. But here we have two types of solution. One is general solution and another is particular solution. In general solution, this is general solution. It is also called as integral of the differential equation. So it is basically a relation between the variables not involving the derivatives, which contains the same number of arbitrary constant as the order of the equation. So we can understand in another word, another way, like if nth order derivative is given in the form of differential equation, then total number of arbitrary constant will be n. So if it is a fourth order derivative, then the arbitrary constants will be 4. If it is a fifth order differential equation, then total number of arbitrary constants will be 5. And in a similar way, if it is nth order derivative, then total number of arbitrary constants will be n. So we shall be discuss it step by step. So here a general solution of this differential equation, this one, is x is equal to a cos 2t plus b sin 2t. Here we find that what is the order? Order is 2 here, and degree of course 1. Degree is nothing but the exponent of the highest order derivative. So here order is 2. It means that there should be 2 arbitrary constants, and we can see here a and b are the 2 arbitrary constants in the solution of the given differential equation. So a and b are nothing but the arbitrary constants. Now moving to the next slide, particular solution of or particular integral. So both are same thing, you say particular solution or particular integral. So in the previous slide what we saw here, a and b are the arbitrary constants, but once we solve the differential equation, after integration, that we will talk about later, what are the different steps of solving a differential equation. So after, as we know that in indefinite integral we are putting c as a constant or k may be constant of integration. So once we are removing c and k by substituting the variables x and y in the solution, general solution of the differential equation, then actually after substituting the value of the constant, whatever solution we are getting, that is called particular solution. So particular solution or particular integral is that solution of the differential equation which is obtained from the general solution of assigning particular values to the arbitrary constants in the general solution. So for an example here, this is the example of a differential equation. Order is 2 of course, and degree is 1 here. Here 2 variables x and y are given, wherein x is the dependent variable and t is independent variable. So t is here independent and x is dependent variable. So x is equal to 10 times cos 2t plus 5 times sin 2t is a particular solution of the differential equation, because here we don't find any arbitrary constants, there is no constant. So when the solution of the differential equation is free from the constants, then we say it a particular solution or also particular integral. Now we shall be dealing with some basic questions, that how to solve the differential equation. So we have to find in the beginning stage the general solution, then subsequently we will talk about the particular solution also. So in this question, what do we find here? That show that y is equal to a times e raised to the power x plus b times e raised to the power 2x plus c times e raised to the power minus 3x is a solution of the given differential equation d3y upon dx cube minus 7dy by dx plus 6y. So this is the differential equation first of all, and this is the solution. Of course this is the general solution, because here a, b, c are the constants. So in this question we have to verify whether the given solution is the solution of the given differential equation or not. So what are the steps we have to follow? Here we find that third derivative means order of this differential equation is 3, of course. So this is 3 times derivative, this is 1 time derivative, and this is the y part. So we actually from the given general solution we will find 3 times derivative, 1 time derivative, and we will put it in the LHS of the given differential equation, and we will verify it if LHS is equal to RHS, that is 0. So let's solve this question. So given solution of the differential equation is y is equal to a times e raised to the power x plus b times e raised to the power 2x plus c times e raised to the power minus 3x. Now we will go for one time differentiation. So we will have a dy by dx, and this will be equal to a times e raised to the power x only, a being constant, and e raised to the power x differentiation is e raised to power x only. Now here e raised to the power 2x, so differentiation of 2x, because what will happen, b times e raised to the power 2x, and differentiation of 2x is 2, so we will write here 2b times e raised to the power 2x. Similarly here e raised to the power minus 3x will be as it is, and the differentiation of minus 3x is negative 3x is negative 3, so plus minus minus here negative, and 3, and then c being constant will be kept as it is. So this value we are going to substitute in the given differential equation dy by dx, and since it is given third order, so d3 y upon dx cube will go for second time, and third time also we will differentiating the same thing. So now second time if you are doing d2 y upon dx square is equal to, again it would be a e raised to power x, this will be 2 2s are 4, b e raised to the power 2x, and minus minus plus 9 c e raised to the power negative of 3x. When you go for the third time d3 y upon dx cube, then what will happen, a times e raised to the power x, 4 2s are 8, b times e raised to the power 2x, minus 9 3s are 27, c times e raised to the power negative of 3x. Now we will take LHS of the given differential equation. So LHS of given differential equation is, so LHS is equal to, we will prove LHS and RHS both equal. So d3y upon dx cube minus 7 times dy by dx plus 6y is equal to 0. So we are going to substitute the d3y upon dx cube, and also negative 7 times here dy by dx, we are going to substitute it. So what will happen, this is d cube, so a e raised to the power x plus 8 times b e raised to the power 2x minus 27 times c e raised to the power minus 3x. Now we have to multiply with negative 7 of dy by dx, so it's a better we can multiply here only. So it would be negative 7 a times e raised to the power x plus 7 2s are 14 minus 14 b times e raised to the power 2x, now minus minus plus plus 21 c e times e raised to the power negative 3x. Okay, we got it. Now we have to write plus 6y, so plus 6 times y. So what is y exactly? Y is the given solution. So y, it's a 6, so it would be plus 6 times a raised to the, a times e raised to power x plus 6 times b raised to the power b times e raised to power 2x plus 6 times c e raised to power minus 3x. Now we just need to add on So 1 time and then 6 times makes 7 times. So we will write here 7 times a times e raised to power x. Now here it is 8 times b and 6 times this. So 8 plus 6, 14. So it would be 14 b e raised to the power 2x. Now here 27. So we will write here negative of 27 c e raised to the power minus 3x. Then we will write this minus of 7 times e raised 8 times e raised to power x. Then this portion minus 14 b e raised to the power 2x, and then 21 times this and plus 6 times this. So 21 plus 6, 27. So plus 27 c e raised to power negative of 3x. So what do we observe? This much, this and this all getting cancelled, plus and minus. So we are getting this 0, that is your RHS. So we can write hence verified. This shows that the given equation, given solution is the solution of the given differential equation. Now moving to the next, we are talking about how to solve a given differential equation. Normally we are separating the variables. Suppose x and y are two variables are given, wherein y being dependent variable and x independent variable. Derivatives dy by dx is given in the given differential equation. Then our first approach should be to separate x terms with dx terms and y terms with dy terms. Both sides of the equation is equal to, and then we will integrate it. That we will do step by step. So what is this method of variable separable? Variable separable means variables are separated. We know that there are two types of functions. We have implicit function and explicit function. So here we are talking about explicit function, wherein variables x and y can be separated altogether. So here we will be dealing with type 1 question. If the coefficient of dx is only a function of x and that of dy is only the function of y, in the given differential equation, the coefficient can be solved using variable separable method. So here what we are dealing with is, if the variables are given, as we know the basic definition of differential equation, that we have x and y. Here y is dependent variable and x is independent variable, and dy by dx is the derivative. Then what we will do, f of x dx means terms related to x with dx can be separated at one place, and the term related to y can be separated at the other place. Even if it is on the left side, it's okay, no problem. We can keep it right side also, that's also fine. And after that, the main step is to integrate it. So if we are integrating it here, then we will get integral of f of x dx plus integral of g of y dy is equal to c, and this is basically the solution of the given differential equation. More precisely, this is general solution because constant c is mentioned. So this is the general solution, but the given differential equation is this much. So here we can take one basic, very basic question for this session, then we will continue in the next session. So this question we have to solve the differential equation xy times dy by d is equal to 1 plus y square upon 1 plus x square 1 plus x square. So what should be our approach? Our approach should be to separate the variables x with dx at one place and y with dy at another place, and we have to integrate it, and then that is the only general solution of the given differential equation. So let's solve this question. So here this is given differential equation. So this differential equation can be written as, so the given differential equation can be written as, if you want to write, we will just go for cross multiplication. So here it would be x times 1 plus x square y times dy is equal to 1 plus y square, then 1 plus x square and dx. This is the first stage. Now in the second stage, we will keep all x with dx at one place. So let it be like this. So firstly, y part, here y and dy is there. So let it be y dy upon 1 plus y square is equal to 1 plus x square dx upon x times 1 plus x square. Now here what we have observed, that we have kept x with dx at one place, y with dy at another place, both sides of the is equal to sign of this equation. This is the differential equation. Now our next step to integrate both sides. So on integrating both sides, we get, so what we shall do here, we will write integration of y dy upon 1 plus y square is equal to integral of 1 plus x square upon dx times x into 1 plus x square. So now this is all about integration. So for doing this chapter, we should have very sound understanding of integration. So how will we integrate this? So for this we can do one thing. If we go for method of substitution, so 1 plus y square, if we go for differentiation of this 1 being constant 0, y square is 2x. So 2x y square is 2y dy. So only y dy is there. So in the left side we can write this way, half times 2y dy upon 1 plus y square. So what will happen here, if we will integrate it, this function now it's integrable, is equal to, we can write this portion here, this one, as 1 upon x plus 1 upon 1 plus x square dx. Why so? Because if you take LCM, so it will match with this. In the numerator, it would be 1 plus x square plus 1. So the same thing you will get here. Now the next step is half times, this will be ln 1 plus y square, and this will be equal to 1 by x, that is nothing but ln x, and it would be how much? 1 plus x square, this will be tan inverse x. So we can write tan inverse x plus c. So this is the only general solution of the given differential equation. But here again we will fix it. I mean we will arrange it in a proper way, so to match the answers. So let's see here. First of all, here it is in log, here it is also in log. So we can take constant of integration also. ln c. Now what is the next step? Next step would be ln 1 plus y square, this would be under root, is equal to, we can take these two as ln cx, and then we can write here ln e and then also e tan inverse x. So what is this basically? If the base and the log both are same, so its value is 1, so we can transform it so that we can have the operation, basic operation, that is log x y is equal to log x plus log y, log x plus log y. So here the next step would be ln root under 1 plus y square is equal to ln cx e raised to the power tan inverse x. So we can remove log both sides. Therefore 1 plus y square is equal to c times x times e raised to power tan inverse x, tan inverse x. So this is basically the general solution of the given differential equation. So we have in the question, solve the differential equation. So you have solved it, and this is nothing but, this is the general solution of the given differential equation. Why general? I have already mentioned, when the constant is there after integrating, then this is called general. Once we will get the value of c after substituting x and y if it is given in the question and returning the value of c, that is called particular solution. That also we shall be dealing with. So for today, in the today's discussion, we have talked about basics of differential equations, its definitions, and different types of differential equations. We have talked about the general solution and the particular solution, and then we solved. We have also verified a given solution is verified by differential equation or not. And now in the last question we have solved a differential equation and we have got basically the general solution. So thank you very much for today's class. In the next class we will be taking some more questions and different types of questions we will be taking. Thank you so much. Thank you.